If advanced civilizations exist, the universe shouldn't look like this. We expect them to leave marks on stars, on systems, on entire galaxies. And yet, when we look out into the universe, it doesn't look like anyone has ever been there. Is there no one to see? Or are we just looking the wrong way? Not long ago, we took a look at how we search for alien civilizations in our episode SETI Explained, where we walked through everything from radio signals to laser pulses, and briefly touched on what's often called Dysonian SETI, the idea of looking not for messages, but for the large-scale engineering projects advanced civilizations might leave behind. Because if someone had spread beyond their home planet, they don't just talk, they build. And the particular thing we expect them to build is a Dyson sphere, or more realistically, a Dyson swarm, not a solid shell, but a vast cloud of habitats, solar collectors, and infrastructure surrounding a star, capturing a significant fraction of its energy. This is also known as a K2 or Kardashev 2 civilization. Now, in that episode we treated Dysonian SETI as one tool among many, but it's also something more than that. It's one of the most direct answers to the Fermi paradox. Because if advanced civilizations exist, and especially if they expand, we shouldn't just hear them, we should see them. And not as a faint signal or ambiguous anomalies, but as something unmistakable, stars that don't look like stars anymore, and galaxies that don't look natural. And yet, we don't. We don't see stars surrounded by obvious megastructures. We don't see galaxies half-converted infrared glowing industrial engines. We don't see regions of space that look like they've been systematically dismantled and rebuilt. And that raises a very simple question. If Dyson Spheres are such an obvious and powerful idea, why haven't we found it yet? So today we're going to take a deeper look at that question, not just how we search for them, but what we should realistically expect to see if they are out there, and what it means that, so far at least, we're coming out blank. Are aliens common, but simply not building these things? And if so, why? We'll explain some of our tools, like the Dyson Dilemma and T, the time-elapse argument, and how that lets us differentiate anomalous objects like quasars as natural rather than artificial. And if such explorations and deep dives are your cup of tea, hit the like, subscribe, and notification buttons, settle in with a drink and a snack, and let's investigate our seemingly paradoxical reality. What could we actually see? Before we can ask why we haven't found Dyson spheres, we need to be very clear about something. What would finding one actually look like? There's a tendency to imagine these things as obvious, like a giant shell blocking out a star. But real Dyson structures don't look like that. They don't turn a star into a black disk, they change its spectrum. A Dyson swarm still lets energy out, it has to. Most of the mass of our solar system is in the sun and very hot. Without a way for that light and heat to escape into deep space, even if the sun stopped fusion at its core tomorrow, we would all melt to death in short order. Inside, the temperature would keep rising as fusion not only didn't stop, but accelerated from growing temperatures, trailing off somewhere over 1 trillion Kelvin. Fusion would eventually break down at super high temperature as particles moved too fast to fuse efficiently. We, of course, would be long dead, as would anything built out of matter. So you must get rid of your heat or you'll burn, and the only way to do that in space is to radiate away as photons of a wavelength appropriate to your temperature. Unless they have advanced clock tech, which admittedly would not be too surprising either, then they are bound by the laws of thermodynamics. So energy does not disappear, gets used and eventually radiated away as heat in a different, longer wavelength, infrared light. Instead of shining mostly invisible light like a normal star, a Dyson system would tend to glow in the infrared, at temperatures somewhere in the range we'd expect for habitats or machinery. Now, we can't take for granted that a Dyson is a set size or appearance, and we'll discuss the exceptions later, but you could have ones that emit in cooler microwave ranges, which reflect a lot of their waste heat into a black hole, or which are built using more exotic methods of power generation or concealment. Moreover, unless they're trying very hard to be concealed, they probably are still emitting a significant amount of visual light too, as well as many other spectrum. So what we're actually looking for is not dark stars, but stars that look wrong. Let's focus on the default case for now. Too dim invisible light, too bright and infrared, or just inconsistent with what we expect for their size, age, and type. Now, how far away could we see something like that? For a single star surrounded by a Dyson swarm, the answer is not that far. astronomically speaking. We could potentially detect strong infrared anomalies within our own galaxy, especially for nearby stars, but as you move farther out, those signals get harder to distinguish from natural sources, like dust clouds, debris disks, or stellar variability. Now, you could confuse a Dyson with a natural effect, think Tabby's star, simply by a disk of debris in line with us that's situated at about the Goldilocks zone distance. But as I noted in that episode years back, you are never looking for one sign of artificiality, you're looking for several in conjunction. A city has hundreds of techno-signatures, but what is going to be easiest to see? Once you spot it, you can turn your gaze more firmly on that star and hunt for others like strangeness and radio emissions, but that first sign might be hundreds of times easier to see than the next few. It's what makes us do a double take and stare for the other clues. As a result, a lone Dyson system is relatively subtle, to us anyway. To anyone with the ability to build one themselves, even with what we consider somewhat basic advanced technology, the sheer skill of detectors they could deploy would make spotting one relatively easy. IR telescopes thousands of miles wide, parallaxing thousands of AU out, make for a powerful eyeball. And if you can build 1,000,000 of those, for a cost that would be a budgetary rounding error for a K2 sieve, you have the ability to spot regular old exoplanets galaxy-wide and monitor each star in the galaxy better than we can monitor our own. All of which is to say, a Dyson swarm is subtle to us, but it isn't actually subtle. It's a star-powered mega-civilization. It's something we might detect in our corner of the galaxy out to maybe a few thousand light years with some luck, but it's not something we're going to spot easily in another galaxy unless it's doing something very unusual. But that's not really what we expect to find anyway. There's no paradoxical mismatch between observation and expectation if only 1 in a million stars has a Dyson swarm. There are hundreds of billions of stars in our galaxy, so even a very large number of civilizations might still produce relatively few detectable examples of that scale. The key assumption behind Dysonian SETI is not that a civilization builds one Dyson sphere, it's that they can build one, they can build many. And once you can build many, the scale changes dramatically. Indeed, as we discussed in episodes like Interstellar City-States, you're not really expecting a bunch of independent Dyson spheres anyway. You're expecting a decreasing concentration of smaller megastructures as you move out from a star, but no real end to civilization. You'd have highways between the stars, with millions of ships moving along them. Not to mention hermit habitats drifting Oort clouds running on fusion reactors or micro-black holes. Dyson swarms around more prevalent red dwarfs would be far slimmer than those around bigger suns, but much like a map of a country, there's no unoccupied space, just variation from ultra-rural to dense downtown. And this Dyson sprawl should get bigger and bigger over time as it encapsulates more and more systems, assuming they keep growing of course, and we'll return to that point later. But if they grow, we'd expect not lone K2 civilizations, but clusters of stars with unusual infrared signatures, regions where energy output doesn't match stellar populations. And if civilization goes further, spreading across the entire galaxy, then the effect should be unmistakable. A galaxy where a significant fraction of the stars have been partially or fully enclosed in Dyson swarms would not look like a normal galaxy. Its structure might change as stars are moved, dismantled, or repurposed. You might see entire regions where stars have vanished, replaced by diffuse, low-temperature emission. The specifics might vary from what we expect, but it would look engineered. So when we look out into the universe, we're not just asking, can we see one? We're asking, if these things exist, why don't we see them everywhere? And that's where the real puzzle begins, the Dyson Dilemma, the Fermi Paradox. But before we delve into that, let's talk about deep time and how it can confuse and help us. And that's where the real puzzle begins, the Dyson Dilemma of the Fermi Paradox. But before we delve into that, let's talk about deep time and how it can both confuse and help us. The timeline problem. Once we move past the question of what a Dyson sphere looks like, the next question is how long it takes to build one, and, more importantly, how long it takes to build many. Building a Dyson swarm is not easy, but it's also not a matter of exotic physics. It's mostly an engineering and logistics problem. You're disassembling planets, asteroids, maybe even stars, and turning that material into habitats, collectors, and infrastructure. Hard, yes, but fundamentally straightforward once you have the industrial base. See our episode Building a Dyson Swarm from Scratch for the technical details. But in our context today, think of it like a highway system or a city. Better technology helps, but is not strictly required. We tend to assume only ultra-high-tech civilizations could build something like this, when it's just likely that having one is what makes you ultra-high-tech, because of the resources it unlocks. The key point is that it's not a billion-year process. Even conservative estimates tend to land on hundreds of thousands to a few million years to spread across the galaxy and begin transforming large numbers of stars. On the low end, for heat limitation reasons, even some amazing self-replicating construction machine probably cannot disassemble a planet usefully in under several centuries. See our Harvesting Plants episode. That might sound like a long time. It is not. A million years isn't long enough to hide, but it is long enough to be seen. The Milky Way is billions of years older than our world. Most galaxies are in that same range. Even if intelligent life only started appearing in the last few billion years, that still leaves plenty of time for civilizations to arise, expand, and leave a visible mark, not just at the galactic scale, but at the supercluster scale, especially as things were closer together back in the day. So in addition to your own galaxy, you can cross over to another, long voyage, millions of years, but there's also stars in between to serve as waypoints and beachheads, and once there, you can work your way across the new galaxy in a million years. Which leads to a very specific expectation. We shouldn't just see finished Dyson civilizations, we should see them in progress, galaxies where some stars are enclosed and others are not, wavefronts of half-enclosed stars where instead of peaking regular stellar ranges or the IR Dyson ranges, you get a big double hump between them on the border, tilting to one or the other depending on where in that border region you are. Or maybe you race ahead to use black holes as free slowdowns and place to expand outward from in that region of a galaxy, so you see smaller ripples but still distinct regions of half-finished transformations, uneven, patchy, and incomplete. Because the process takes a million years, and civilizations had billions of years to do it, then we should mostly see our random snapshots of that process, not just endpoints, but civilizations caught in the act. And yet, when we look out at other galaxies, we do not see that. We don't see the signs of large-scale engineering underway. We don't see expansion fronts. We don't see the fingerprints of a process in motion. And that absence matters, because it's just we're not just missing the finished examples, we're not seeing the process at all. Looking out is looking back. And there is another layer to this, one that turns the entire universe into a timeline. When we look further away, we are looking back in time. Light takes time to travel, so when we observe a galaxy a billion light years away, we are seeing as was a billion years ago. 2 billion light years away, 2 billion years ago, and so on. Though beyond that, for simplicity, we usually say light that left X billion years ago, because the Hubble expansion effects start to seriously kick in. Light that arrives to us now from 3 billion years ago would have left when that source was about 2.7 billion light years away, and now is about 3.3 billion light years away. And if we sent a reply, they would get it in about 3.8 billion years, when they themselves were about 4.3 billion light years away. This gets increasingly worse, and the CMB radiation left over from not long after the Big Bang is arriving to us today, 13.8 billion years later, from places now 46.5 billion light years away. Since that can get confusing, even for astronomers, we usually switch to talking about the age of the light we're seeing, or its redshift at these kind of scales. Fortunately, most of the region where we expect light to have had time to evolve and grow to galactic proportions is much closer. We don't really need to worry about light that's 10 billion years old, because at that point in cosmic history, only a small fraction of rocky planets had ever even formed, based on stellar metallicity, and those were likely fairly sparse and resource poor. More importantly, a 10 billion year old signal does not imply a 10 billion year old civilization. If all you found is a newly formed planet, it takes time for life to emerge, evolve, and reach technological capability there. So if we're looking at something 10 billion years in the past, it is probably not artificial. And that's a point worth remembering for later. Anyway, this gives us something like a historical record of the universe. Now, suppose Dyson building civilizations began appearing, say, 4 billion years ago. Maybe that's when enough heavy elements existed, or when planetary systems stabilized enough for life to commonly arise. If that were the case, then we expect to see a very specific pattern. Nearby galaxies, representing the present day, might show signs of large-scale engineering. More distant galaxies, earlier in time, would show fewer. and beyond a certain distance, corresponding to before those civilizations emerged, we would see nothing at all. In other words, there should be a gradient, a kind of civilization horizon, where the further back you look, the less evidence of large-scale engineering you find. This is essentially an extension of what we call the time elapse argument, or T. Artificial phenomena should become rarer the further back in time we look, because they haven't had time to form and expand yet. We've seen this pattern with natural phenomena. Quasars, for instance, were once seriously considered as possible alien beacons, but they turned out to be far more common in the distant universe than nearby, not because they've disappeared, but because we're seeing them at different stages in cosmic history. They peaked around 10 billion years ago, during what we call cosmic noon, when star formation was also at its height. That year is also when we start to see large amounts of population 1 stars, stars like our Sun that contain more than trace amounts of heavier elements. In astronomy, we call all elements heavier than hydrogen and helium metals, even though most of that is oxygen, carbon, nitrogen, and similar elements. After the Big Bang, the universe is almost entirely hydrogen and helium, and even today, most of the helium we see, both in space and inside stars, dates back to that early period, not from stellar fusion. A quick note there. Population 2 stars, those older metal-poor stars, likely couldn't form rocky planets at all, but the appearance of population 1 stars does not mean Earth-like worlds suddenly became very common. Early population 1 stars still had far fewer heavy elements than our Sun, and certainly less than stars forming today. But for Dyson scale engineering, we'd expect the opposite trend. Not more common in the past, but more common closer to the present. And not just in frequency, but in appearance. Different epochs should look different. Earlier galaxies should look entirely natural. Later ones should begin to show signs of large-scale modification. And yet, we don't see that. Galaxies look broadly consistent with what we expect today from natural processes across vast stretches of space and time. This is also why dark matter and cosmic voids don't work. Even though cosmic voids actually are growing larger with time, because we can clearly see them back before any technological life is possible, so they cannot be artificial themselves. At least any in this universe, but let's say the notion of civilizations arriving from precursor realities, future times, or parallel universes for other days. There's no clear boundary where natural galaxies transition into engineered ones, no obvious epoch where large-scale artificial structures begin to appear, and that absence of a time pattern reinforces what we saw earlier. It's not just that we are missing Dyson Spheres, it's that the universe doesn't look like they've ever been common at all. The Dyson Dilemma. All of this leads us to what I often call the Dyson Dilemma. At its core, it's a very simple idea. If civilizations can build Dyson spheres, and they tend to expand, then the universe should already look very different. And even if civilizations are extraordinarily rare, say only one per galaxy every couple billion years, this problem does not go away. Because then the real question isn't why we look up at the night sky and see no civilizations. It's why we see any stars at all. They should, long ago, have been encased in Dyson swarms and rendered invisible to our eyes. The dilemma rests on a handful of assumptions, not exotic ones, just fairly reasonable extensions of what we already know, and thinking through them really changes how we look at life, the universe, and everything. In fact, working through these ideas at the original episode is what led to the follow-up, and in many ways, this whole channel. So, what are those assumptions? First, that building a Dyson swarm is possible, reasonable, and desirable. Not easy, but possible. It doesn't require new physics, just time, energy, and industrial capacity. You don't build it all at once. You start small and keep adding to it as need, desire, and ability intersect, the same way we build cities or infrastructure. It's like the pyramids. You can achieve an enormous amount with enough cheap, expendable labor fueling your ambition. In this case, presumably robots. Though if you've got all Dune and gotten rid of them, you can still build a Dyson. Second condition, that interstellar travel is possible, even if it's slow, and that colonization is practical. You don't need faster light travel, it helps, but even moving at a small fraction of light speed, or sending automated probes, it is enough, given time, to spread from star to star. You can even do this at well under 1% of light speed, what we call colonizing the galaxy, and we have solid designs under known physics that could achieve that. If faster light travel is possible, that doesn't solve the problem, it just exacerbates it, by making expansion even easier, but we'll come back to that. Third, that there isn't some vastly superior energy source that makes stars irrelevant. Because if stars remain one of the best large-scale energy sources available, then surrounding them to capture that energy makes sense. And this alternative has to be much better. Even something like black holes as power sources doesn't remove this issue. You still need to feed them, reshape systems, and deal with waste heat. You still end up with a sprawling, energy-intensive civilization altering its environment. You'd probably still encapsulate those stars too, waste not, want not. If a niche can be self-sustaining, someone eventually fills it. On the other hand, if you can summon and dismiss energy at will, then yes, you might not need a Dyson swarm. We've also removed the constraints on growth entirely, and expansion becomes even easier and more extreme. The fourth assumption is that fast light travel, or access to other universes, is not trivially easy. Because if there are nearby universes, just one step away, filled with fresh resources or even Earth-like worlds, then you might expand there instead of across interstellar space, as we looked at in colonizing the multiverse. Why spend a century on an arc ship to a desolate hellhole around an alien sun, where you can step into an uninhabited paradise planet and its trillion Earth-identical clones? Though even in that case, you'd still expect at least your home system to be heavily developed. Possibly with a full Dyson swarm, you certainly have the resources to do it. The fifth condition is that civilizations do not inevitably wipe themselves out. Not that none ever do, but at least some survive long enough to expand. Because in the Fermi paradox, it only takes one civilization inside our light cone that chose to grow and didn't stop. And, sixth and last, that civilizations tend to grow when they have the resource to do so comfortably. And this is one worth dwelling on for a moment. Comfortable growth. Not infinite growth, not recklessly, but if expansion is possible and beneficial, then at least some fraction will pursue it. And this pushes back against a certain amount of neo-Malthusian thinking. Human population has trended upward over the last few centuries, with technology steadily expanding our ability to produce more. At most, we see brief dips during major catastrophes. Individual regions flatten out or shrink, often due to culture, economics, or migration. And we have historical examples like the Black Death from earlier periods. But globally, the long-term trend has been upward, and those trends are highly dependent on conditions. Access to birth control probably lowers growth rates. Access to fertility treatments or life extension should raise them again. Lifestyles matter a great deal. People often point to wealth, urbanization, or crowded environments as reducing family size, but those are oversimplifications and often very misleading ones. The effects are tied more to cost, timing, and lifestyle than density itself. Historically, powerful individuals often had large families, and modern data is far less clean or consistent than people assume. In the US, billionaires average around 2.3 children, compared to roughly 1.6 in the US overall, and about 1.8 for the upper middle class. People don't start families on accidents as much, and they often start them later because they are focused earlier on education and career. And that varies by country, region, and generation, but that's the point. There is not a universal rule. We cannot assume there is one for all of humanity, past, present, and future, let alone aliens that might lay eggs or have litters. We should assume Darwinian evolution predisposes species to have higher birth rates than are required to maintain their number with technology. Everything beyond that is less certain and probably not universal. Beyond Darwin, which may not be a limit on civilizations anyway, the only universal I can pin down is that technology increases both options and overall prosperity. If you imagine a future human civilization with abundant new territory, robotic labor handling most of the work, lifespan stretching centuries, and multiple paths to reproduction, whether biological, assisted, or artificial, it becomes very hard to maintain long-term negative growth without deliberate cultural pressure. Aliens are not human, but we should assume technology also makes them more prosperous and less prone to dying from natural causes, which traditionally are getting eaten by something bigger than you, or by billions of things smaller than you. Inside that species, us or them, we should assume that any culture or subculture that does suppress its growth risks being replaced over time by others that do not, external factions looking for elbow room or internal factions who disagree. That's all you need. We'll talk about some of the workarounds later, but even if a small percentage of the civilization meets those conditions, then over billions of years they should spread, from one system to the next, building Dyson swarms as they go, forming an expanding wave of visible change. Stars dimming in visible light, galaxies becoming infrared bright, structures spreading outward over time. Even at very low speeds, this process should fill a galaxy in a few million years, which is nothing on cosmic timescales. It's just a blink. And not just one galaxy. A billion-year head start could place a whole supercluster in someone's grasp by now, and it's very hard to hide a supercluster. Nor is any coordination needed over many light years, for the same reason various Paleolithic tribes of humanity did not need to phone home to some tribe they split from 10 generations back before crossing into new lands. They expand because there's no reason not to and plenty of reasons to do so. If this happens even rarely, then across millions of galaxies we should see it somewhere. Somewhere nearby, somewhere distant, somewhere in progress. We don't. We don't see stars as being expanding patterns. We don't see galaxies partially converted. We don't see centers of that wave moving outward. And that's the dilemma. Either those assumptions are wrong, and in most such scenarios you still get visible mega-civilizations, or technological civilizations are so rare that, even across billions of galaxies and billions of years, almost no one has ever reached that stage. And I, for one, tend to suspect it is the latter case. Alternative paths, civilizations that do not expand. One possibility, of course, is that we're asking the wrong question. We tend to assume that once a civilization gains the ability to expand, it will do so, spreading outward, colonizing new systems, and eventually building Dyson swarms around star after star. But that assumption rests on a very human model of behavior. There are other pathways. A civilization might choose, or be forced, to remain localized. Consider a civilization that possesses the technology to begin spreading out to the stars, but notices there is no real benefit coming beyond prestige for settling stars beyond a certain distance. It can't really maintain control over more than, say, 25 light years reliably, and it's worried that colonies being seeded beyond that are inevitably going to diverge into mutant cousins with opposing interests, and they have now surrounded themselves on every side with potential enemies, ones they actually funded the creation of, because interstellar colonization might be practical but never cheap and easy. So instead of spreading across the galaxy, they might focus on consolidating resources closer to home. It might strip mine nearby systems using dumb robots, dismantling small moons, harvesting asteroids, and pulling material from a wide surrounding volume, rendering it a desolation zone that could never be strongly colonized and would limit any invader trying to live off the land. Then they concentrate that mass and energy into a relatively compact region, maybe one star system, but maybe wider. You could imagine something like an interdiction bubble, a large zone around a civilization that has been deliberately cleared out. No easy resources left, no nearby systems capable of spawning new competitors. Ragtag civilizations might persist there, but a fleet could sweep by occasionally and deal with anyone who is becoming a real threat. A kind of engineered desert, not because they couldn't expand further, or because they don't want to, but because they've decided they can't. Anyone who goes far away ceases to be them in a few generations. Inside that bubble you might have one system, or a cluster of systems, packed with enormous amounts of matter and energy, tightly controlled, heavily developed, and relatively self-contained. Outside it, very little, again the desolation zone. That changes what we expect to see. Instead of a wave of expansion sweeping across the galaxy, leaving a trail of Dyson systems behind it, you get isolated pockets. Civilizations separated by vast distances, long gaps where nothing is happening. And if expansion beyond that bubble does occur, it might be rare, slow, and difficult, requiring a leap across thousands of light years, followed by the same process repeating again. A lot of fairly impressive civilizations, by our standards, might hide in the desolation zones, tolerated to a point, but with our current capabilities, we would not likely see them. Over billions of years, you could still end up with multiple such pockets scattered across the galaxy, but they would be sparse, they might not line up in the obvious pattern we could easily detect. This kind of developmental pathway does not eliminate Dyson Spheres, it just makes them harder to find, because they are not part of a continuous galaxy-spanning process. They are isolated and concentrated, and isolation is much easier to miss. That is just one example, and we examined it a few years back in our chrono scenarios and interdiction episodes. People have suggested many and more probably do exist. Energy, efficiency, and the problem of waste heat. Another common idea is that advanced civilizations might simply be too efficient for us to notice. That instead of glowing brightly in infrared, they found ways to minimize or redirect their waste heat. perhaps dumping it into black holes, radiating at extremely low temperatures, or even exporting it out of our universe entirely using some form of exotic physics. And it's true that more advanced technology gives you more options. For reference, most of Earth's waste heat comes out between about 5 and 50 micrometers, right in the mid-infrared. That's often used as a baseline for Dyson swarms, not because it has to be that way, but because it's a natural temperature range for a system like ours. But there's no reason to assume alien biology or post-biological systems would match that. A civilization might build nested structures, multiple layers of energy capture and reuse, stepping waste heat down to longer and longer wavelengths. That's the idea behind something like a Matryoshka brain, where energy is reused repeatedly at lower temperatures, with each outer shell operating more efficiently than the last. They might operate hotter, they might operate colder. They might spread the emission across multiple layers, each one radiating at different wavelengths. But there are still limits. One does not simply handwave thermodynamics away. Energy used is energy that must eventually be disposed of, and while you can choose how and where you radiate that energy, you cannot simply eliminate it, not without invoking entirely new physics. And even if you do push toward lower temperatures, you run into practical constraints. Making your waste heat colder means making your radiators larger, much larger. In practice, you probably don't go much below about 5 Kelvin, roughly 500 to 600 micrometers, before your radiators become so large they stop being useful. For our own sun, you'd have to go out to around 10,000 astronomical units, on order of a couple of light months, before the background radiation from the galaxy starts to rival the sun's own output. Beyond that point, your structure isn't just radiating, it is also absorbing. And once you reach that scale, you're no longer gaining efficiency, just building something bigger than the environment will reasonably allow you to use. That limit also shifts over time. Earlier in the universe, during periods of higher star formation and activity, the ambient radiation was higher, and the cosmic microwave background itself was warmer, so older civilizations would have had an even higher minimum temperature floor to work with. All of which is to say, we don't know exactly what wavelength the Dyson civilization would emit at. We do know this: it should emit, and not just a faint trickle, but a large-scale structured signature of energy use. It is the nature of a civilization and of people that they would like to get something done, and energy helps with that process. Therefore, if there's energy available, they will want to utilize it. And all of that leaves a mark. I dare say if they keep finding new and better technology that makes it easier for them to evade these rules, it will still leave marks, even if it's only a civilization so confident in their ability and immensity they cannot be bothered to hide themselves, or their ego doesn't permit it. So advanced civilizations might not look exactly like the simple Dyson swarms we often imagine, but they still obey the same basic rules. They can shift their signatures, they can redistribute them, they can reduce them in certain ways, but they cannot make them disappear entirely. Intelligence will alter its environment to suit its own goals, and if it isn't, then those brains are a waste of energy. To hide is giving up the very advantages that made them advanced in the first place. To be masters of nature, ready and able to carve their galaxy into a testament to their ambition, yet forced to cower from some unseen predator. And they may consider that too high a price to pay for existence. Civilization does not usually end because one thing goes wrong. It ends because one rare catastrophe arrives before anyone has built the tools, backups, and redundancies to survive it. Ice ages, solar flares, rogue planets, supernovae, lost archives, failed recoveries. These are not just disasters. They are stress tests for whether a civilization has become durable. That is the idea behind my new Nebula Plus collection, Cosmic Catastrophes and Survival. It gathers my Nebula-exclusive episodes on extinction risks, planetary disasters, civilization backups, and rebuilding after collapse. This month's new edition is Nearby Supernovae. Could one destroy Earth, and could we stop it? Where we look at whether exploding stars have threatened Earth before, which nearby stars might eventually explode, and whether a future civilization could shield itself, move the danger away, or harvest the aftermath. If that sounds like your sort of rabbit hole, you can find the full collection on Nebula, along with years of SFA exclusives, collections, bonus episodes, and regular episodes early and ad-free. My link or the QR code gets you 50% off an annual plan, or 40% off lifetime access. The Silence of the Spheres. If the thermodynamics are sound and the timelines are short, then we are left with the final set of explanations, behavioral ones. The most common is that civilizations simply choose to stay quiet. They do not expand, do not build and make structures. They optimize, turn inward, or deliberately hide. But that runs into some serious problems. First, hiding is expensive. It means limiting your energy use, your expansion, your visibility. It means giving up the very advantages that made you an advanced civilization in the first place. You don't do that casually, you do it because you feel threatened. And not by civilizations like us, by ones of your own level or greater. But more importantly, you cannot unring the bell. Any civilization that's been around for millions or billions of years would have been visible long before it decided to hide. You don't need to hide from us, you hide from bigger and older civilizations. And K2 civilizations can deploy telescopes in such scale and quantity they could track every star and planet in the galaxy. Not just through radio signals, but through biosignatures, oxygen atmospheres, chlorophyll, chemical imbalances that indicate life. Earth has been visible that way for over 1 billion years, so any older civilization already knows we are here, and the same is true across the galaxy. Hiding now doesn't erase that. It just means closing the curtain after everyone already watched you move in. You decide to build a secret bunker just outside town, but used bulldozers and explosives to excavate. And the galaxy were full of civilizations doing this, they wouldn't be hiding from us, they'd be hiding from each other. Which raises a much harder question. Why is everyone hiding? Why is every civilization across billions of years choosing the same strategy? If some do it out of fear of the Dark Forest, what about the terrible mega-civilizations as the wolf they're all afraid of? Have they been cowering on their homeworld for 1 billion years, thinking something bigger was waiting for them too? They've all been hiding from their shadows. But even then, they're not all eternal cowards. You don't need all civilizations to expand. You just need some, and that brings us to growth. We ought to assume that advanced civilizations outgrow expansion, that they stabilize, stop reproducing, and turn inward. But that's not a universal rule. Quite the opposite would seem to be true, that evolution tilts strongly to growth, and even then, what really matters is that across millions of species, and millions of worlds, and millions of generations, there is likely no single rule. And once you add abundant space, robotic labor, long lifespans, and multiple ways to reproduce, biological or artificial, it becomes very difficult to suppress growth indefinitely without deliberate effort. And any culture or faction that does suppress its growth risks being replaced by others that do not. Over long timescales, expansionists win. You don't need everyone to expand, you just need one group that keeps going. And that brings us back to the real problem. Because even after accounting for observational limits, and interpretation errors, and alternative development paths, one thing still stands out. We don't just fail to see Dyson Spheres, we fail to see the pattern they would leave behind. We don't see galaxies in mid-transformation, we don't see gradients over time, we don't see regions that look systematically altered. The universe doesn't just lack megastructures, it lacks the messiness we'd expect from civilizations in the process of building them. If Dyson Spheres were common, the universe wouldn't just be quiet, it would be uneven, patchy, and in progress. Instead, what we see is something far cleaner, a universe that still looks natural, that still looks untouched. And every explanation we come up with for why they aren't here is really a guess about our own future. Needless to say, that does not prove there's no one out there, but it does suggest at least one of our assumptions is wrong, about how civilizations grow, about what they build, or about how long they last. And until we understand which, the silence of the stars isn't just a mystery, it's a clue.